In this module of Chapter 2 on life tables, Module 2.9, I will describe the use of the life table as a population model with zero population growth. It's referred to as a stationary model. I show a property of this model referred to as a life table identity, in which the number of years lived in a population equals the number of years remaining. Consider this table showing the relationship of the age distribution, denoted CX, in a stationary population with 4 age classes, to the time to death distribution of its members, denoted DX star. I use 3 subtables here to illustrate this identity. The first subtable shows the stationary population with several columns from the now familiar single decrement life table. Column 1 contains age X from 0 to 4. Column 2 contains NX, which gives the number in the population age X, which is identical to the number of individuals surviving to age X from the initial number of 40. This is where the population model and the life table model begin to connect. That is, column 3 shows this relationship in terms of an LX schedule, in which the reduction in numbers of individuals with age in a stationary population will be identical to the reduction in survival according to the life table LX schedule. This connection is again shown in column 4, which contains the fraction age X in the stationary population CX. Note that these fractions are identical to the fractions that each age class in the NX column represents out of 100. In other words, there are 40, 30, 25, and 5% of the stationary population in each of these respective age classes. Now suppose we take a random sample of this population in which the fraction from each age class is represented in exactly these same proportions. Thus, this top row is what we refer to as a captive cohort, in which individuals in this group are of mixed ages that will be survived downward in this table according to the LX survival schedule. So the first age iteration, we see that there's 0.3, 0.25, and 0.05, and then 0.0 of the 4 age classes survive to the next epoch. Then of these, there's 0.25, 0.05, and 0.0 survive. And then this is again repeated until all individuals from this captive cohort have died. Survival of these captive groups of mixed ages, when summed within successive time periods, creates a new survival schedule, denoted LX star, as a captive cohort with survival of 1.0, 0.6, 0.3, 0.05, and 0.0 for the successive time periods since capture. Although these numbers appear to have no connection with the original hypothetical population, an identity appears when the fraction dying in each of these epochs is computed from the differences in survival, as shown here as the death distribution of the captive cohort. That is, the fraction of deaths from 0 to 1 equal 0.4, from 1 to 2 equals 0.3, from 2 to 3 equals 0.25, and from 3 to 4 equals 0.05. This step reveals a connection between the age structure of a stationary population and the distribution of deaths of individuals within it. Here's how this concept can be applied to a hypothetical population. Question: how to determine the age structure of a stationary population without knowing the age of any single individual within it. Consider sampling from this hypothetical population with individuals represented as these circles. An age structure exists in this population with individuals' ages color-coded so that we see that we have ages 0, 1, 2, and 3 with these different color codes. Let's sample 100 individuals according to their proportion in the population. We see that there's 40, 30, 25, and 5 in the age classes 0, 1, 2, and 3, respectively. Now let's suppose the individuals were in a cage and are survived forward as a group, and we record the total number of deaths each day. So we have deaths from day 0 to 1. In each of these age classes contribute a different number to the death count according to their age-specific survival rates. Then from 1 to 2, followed by 2 to 3, and finally survival from 3 to 4. We now see the identity with 40, 30, 25, and 5 individuals in the sample population at ages 0, 1, 2, and 3 respectively equals the death distribution of 40, 30, 25, and 5 deaths at post-capture times of 0, 1, 2, and 3 respectively. This is illustrated in a hypothetical life table population for humans. You see on the right the fraction exactly between 90 and 95 years old in the population equals the fraction that have exactly 90 to 95 years yet to live. This ends Module 2.9 on stationary population models and the life table identity. More detailed information on this topic is contained in Chapter 2.